Okay, so this is where the fun really begins in this course with Taylor series. And we're going to look at an analytic solution, which we've already been looking at. Then we'll look at the Taylor series approximation, one of those being the Euler method. And then we'll look at error analysis and we'll compare like the Euler method, which is the two-term Taylor series, to longer Taylor series, which are more accurate. And this information is from numerical methods in biomedical engineering. So we're switching now from Math Insights website to this book, Numerical Methods in Biomedical Engineering, just for a short time. And he has a very nice chapter on, it's called Concepts in Numerical Analysis, where he goes over many types of Taylor series and finding derivatives and subtracting Taylor series from Taylor series and so on. So if you're interested in Taylor series, I'd suggest that you read that chapter. We aren't going to go so deeply into Taylor series, but anyway, you can get that book online by just typing Done Biomedical into the library search engine. And then here it is online. And then you can go to chapter 3 if you're interested in more details. Okay, and I just wanted to mention one thing because it's on the quiz. We've been talking about first order growth rate equations. So that'd be dC over dt equals mu times c, such as microbes, where you have the growth is dependent on the previous population. But there's other types of growth rate equations in biology. For instance, tomatoes, some of you work out at the Controlled Environment Ag Center. Tomatoes are what's called indeterminate. They don't have a final, at least these tomatoes, they don't have a final length. And so they grow like 40 feet and they keep extending them around the greenhouse. So that would be a zero order equation where dC over dt is a constant. You can see that it's not mu times c, it's just, you could say it's just mu. Okay. And then first order growth rate equations would be like cell division. Okay, so we last time talked about the analytic solution for the first order growth rate equation. And so that would be this exponential solution where we have C0 e to the mu t. And so you worked with that on your previous homework. And the Euler method is a numerical solution. So this is the analytic solution. I also call it the continuous solution because the numerical solutions are calculated at specific time steps, okay? But you can see that it's not a true solution to the differential equation. It's just a rearrangement of it where the concentration at time 1 is C0 times mu times C0 times some delta t. So delta C is mu C delta t. And then if you want to know C1, it's C0 plus mu C0 delta t. So that's the Euler method. And those are the first two terms in the Taylor series. So I just wanted to kind of lay the groundwork here. And also, you can see that the continuous model is this line. The Euler method underpredicts the growth, and we'll talk about why later. So that's the first two terms in the Taylor series. If you use three terms in the Taylor series, you can see for this simulation, it almost is exactly right. And likewise, four terms in the Taylor series. So if you use more terms in the Taylor series, you'll have it closer to the exact solution being the analytic solution or the exponential solution. So here's the Taylor series. And in our case, our function is C e to the mu t. And so, we could use the exponential to calculate it, but also we can represent it with this series. And sometimes it's just convenient to represent things with a Taylor series rather than using the exact equation. For instance, in irrigation simulation, I know we use the Euler method quite a bit. You wouldn't use it so much in biology. We just use the exponential solution because it's more accurate. Okay, so but anyway, the Taylor series is the function times f at some t0. So this is f at time t, and we have f at t0. Then we have the derivative at t0 times t minus t0. Then we have the second derivative at t0 times t minus t0 squared over 2. Then we have the third derivative of t0 times t minus t0 cubed over 3 factorial. So that's an approximation of this solution. And in our case, we're going to use h as the time step. So that's like dt. That's like t minus t0. So what we're doing is we're calculating the change in concentration from t0 to t. And if you're interested in more on the Taylor series and derivations, I can recommend this website. It's very nice, very simple. He does a really nice job of explaining things, or maybe not explaining things and just making it look simple. Not sure which. Okay, so we have to take the derivative of this equation, C0 e to the mu t. And so here's the function, C0 exponent mu t, or e to the mu t. And then the derivative would be mu times C0 exponent mu t. Then the second derivative, this is really nice for the Taylor series because it's this kind of solution. So we basically have the same thing over and over. We just add a mu squared, a mu cubed, a mu to the fourth to get higher order derivatives. And what we're going to do is we're going to substitute in for the function and the derivative and the second derivative. We're going to substitute in these values, and we're going to use the Maclaurin series to expand around 0, and the exponent of 0 is 1. So the nice thing is we can get rid of all these exponent mu t's. So we take the exponent at 0, we get rid of it, and then we have C equals the Taylor series for this exponential equation, C0 plus mu C0 h plus mu squared C0 h squared over 2 plus mu cubed C0 h cubed over 3 factorial, and so on. So if you remember, I told you that the first two terms in the Taylor series are the Euler method here, which you can get by just rearranging the differential equation. And then the next terms give you more accuracy. So this doesn't give you very good accuracy, but if you use the third term in the Taylor series, it gives you higher accuracy. And the fourth term gives you even higher accuracy. And actually, you can see that you could go on for 8 terms or something. Okay, so we're going to be talking about different types of error next time on Monday. And there's 2 types of error. There's round-off error and truncation error. Now, people are always confused about those. So that's why I put it in red. When you leave off terms in the Taylor series, it's called truncation error because you're truncating the Taylor series. Yes?
Oh wait, no. Just the mu squared and mu cubed, the 2 and the 3 on the presentation didn't go up. So I didn't know if it's exponent or just multiplying.
Here?
Yeah.
Okay, where did the mu not go up?
On slide 11.
Oh, previously. I think it did go up.
There's other parts where it goes up. So I was just confused.
Oh, okay. Well, it's a good question. Because this is confusing, and it just takes looking at it for a while. So if you do see an error, let me know. Okay. So we can put this in our same code. And so I'm going to have 5-minute time steps, dt, that's h. I'm going to have 7 steps. I have to say what my initial concentration is. I don't need to worry about anything else because I'm just starting with a concentration and then simulating. I'm going to specify what my mu is. So I don't need to calculate it. I just specify what it is, and that's how we'll be operating the rest of the course. So we'll assume that somebody's already done an experiment to characterize the mu. For example, when I was in algae research, this guy set up this huge table with different levels of light, different levels of temperature. So it was like temperature this direction, light this direction, light intensity, all these little flasks. And he would measure the algae concentration, every day or every half day. Um, and then he would come up with mu values, and we would use those in our simulations. So, but we'll assume that we've already done that. And then we're going to set up B, and I'm not sure I need B actually. But B exponent, that's the exponential solution. Then B Euler, then B Taylor 3, which is 3 terms in the Taylor series, and B Taylor 4, which is 4 terms in the Taylor series. And so then I can put my arrays in the loop. So just like we started with B exponential equals B exponential I minus 1 times exponent of mu times dt. So that's the exact analytic solution. And then B Euler, we have B Euler at I minus 1 plus mu times B Euler. So you can see that we've got each array in its own equation. So we're consistent. So the Euler is always dependent on the previous Euler. Taylor 3 is always dependent on the previous Taylor 3. Then you can see that the Taylor three-term Taylor series is the Euler solution for the first 2 terms, but then we just add one more term for the third 3-term Taylor series. And then we have the 4-term Taylor series with just one more term. And so what you can see is similar to the graph I showed you before. We have the Euler method here. It's not very accurate at this 5-minute time step. So remember, I had mu as 0.1 before in that other graph, but I had like 1 or 2-minute time steps. So the Euler was close to the actual solution, and I'll show you why. But when their time steps get bigger, the Euler method becomes less accurate. And then you can see that the Taylor series, 3-term Taylor series is almost like the analytic solution, which is the blue line. But the 4-term Taylor series, even with these big time steps, is almost perfect. Okay, so you can see that with higher order Taylor series, you have higher accuracy. Okay, so what is going on? The Euler method is a linear approximation. It's just using the slope at the beginning of the time step. So, and then it's underestimating. It's not getting the curve, right? It's just doing the increase according to the initial slope. The third term is the second derivative. And so it gives you the curvature. Remember, that's the f double prime is the third term. And the fourth term is the third derivative, which gives you the rate of change of curvature. So the fourth term, by using the curvature and the rate of change of curvature, it has an exact solution. That doesn't mean it's the exact solution. Always, you could use the 5th order term too. Okay. So here's the problem with Euler. I already explained it, but you're using this, and let's say you have 10-minute time steps, okay? You're using this initial slope here at the value of C. Mu times C is the change, mu times C times delta T. You're using this initial value of C, and then you're using that same slope to get to the next time step. So you can see that it's drastically underestimating what's really going on by using that initial slope. Now, if you had curvature like the third term, then you're going to get up closer. And then if you have the rate of change of curvature as you go through the time step, then you're going to be almost exactly right. So what you've probably seen is the longer the time step, the greater the error. And so there's a choice Are you going to use a higher order Taylor series, or are you going to use smaller time steps? And usually you just use smaller time steps in my type of research because I don't have models that take a huge amount of computer time. Okay, like I have daily estimates of things and I run it for a season, which is 90 days. But if you had, like some sort of imaging where you have millions of cells and you're modeling it, every 10 minutes or something, then you would really worry about computer time. And you think about, well, do I want more steps or do I want higher accuracy per step? Okay. So this is just saying what I already said. It may save computer time to use a higher order Taylor series instead of very small time steps in order to increase accuracy. Okay, so that's it for this lecture. Are there any questions?